All right, so our take-home final. You're going to submit your work as usual, including an Excel file or a spreadsheet file. I would like the spreadsheet file to be something where I can see your formulas. I don't really want a phone picture of your screen or anything like that, or even a PDF. I would like it if when if you're getting your file from Google Sheets, there's an option to download the file as an Excel file. So that's what I want you to do, and then upload it to Canvas. The option is, it's gonna make me sign in. Gross. I don't want to sign in. It's gonna make me do two-factor authentication. When you go up to file, like where you would save it on Google Sheets, there's an option to download the file, and you want to pick as an Excel file. You need help finding the exact option in the menu, let me know. Come see me in office hours. I'll help you with it. So here's the gist of the rules. It's going to be due next Friday. So you get a week and 2 days. You get 2 full days after the in-class test. So you have plenty of time to work on it. It's only 2 questions. The rules for this, this is going into the exam category, so you're going to have a total of 120 points in the exam category. Every question, every page on the test is 10 points, and then each of these 2 problems is 10 points. So they're weighted the same as an entire page on the in-class test. You're allowed to use notes, you're allowed to use textbooks, you're allowed to use previous homework problems we've talked about, you're allowed to come talk to me about it. You can work with other students. You can even use outside resources like YouTube videos. And I hate to even say this out loud. You can even ask AI to explain a concept to you. I don't recommend that because I don't think it does a good job of that, and it gets it wrong roughly 20% of the time. And you don't want to bank a big chunk of your grade on was it right or wrong. So I highly recommend not going that route, but you can ask it for help. That's okay. It's not against the rules anyway. What you can't do is plug the specific question in and turn in what the AI gives you, or even plug in the same question, but you changed some numbers. Like that's still asking AI to do the question for you, even if you changed some numbers and then changed it back when you went through and did the math yourself. What you can't do is copy another student's work. So where I draw the line from that is, do you understand what you're turning in? And the way that I test that, if there's any question about that, is that, okay, if I gave you a blank piece of paper and this problem, could you at least get started going down the right path? If you can't, if you sat down with a piece of blank paper and you would have no idea where to start, but you turned in a complete problem, that's an issue. That's cheating. That's plagiarism, right? Working in groups is fine as long as you're working together and you understand what you're turning in, right? It's a very fine line. Usually, I know you all well enough by this point, so I know who's working together. So I look at everybody's tests next to each other to see how closely aligned they are. They shouldn't match up exactly because you should be writing your own stuff down. So if you want to make sure that you don't fall into the trap of, well, we worked together and I'm not sure where the line is between copying, have somebody explain it to you verbally. Don't have them just show you their paper. If they explain it to you verbally and then you're able to do the work on your own, that's your own stuff. That's good. That's perfect. That's how you're supposed to work together. If they're done with the problem and then they say, hey, can I see what you did here? And you look at it and say, oh, I missed that step. That's getting a little hazy, but at least most of it's still your own. But if you're just straight copying things down, that's where things get sideways. We don't want that, right? So when in doubt, do it verbally. Because if somebody can explain it verbally and you can understand it, and then do the work on your own, you're good. Okay. This is less of an issue now, but I do still see things pop up on various online forums, Reddit, things like that. Don't go ask Reddit to do your problems for you either. I see those, and they show up when I Google. If I just Google the problem, if I just use a search engine with the text of the problem that I wrote, I shouldn't be seeing any exact matches show up, right? If I see exact matches show up, I have to go look at timestamps. I have to figure out who answered what and match it to somebody. So it's a lot of work for me. I don't want to do that. You don't want me to do that. Don't post the press questions online to an AI or anybody else. Don't go to the tutors for help. They could help you, but I don't want to put them in a position. It's not fair to put them in a position where they're trying to decide how much help is appropriate. Right? So that's just not fair to the tutors. So don't do that. The tutors all know my take-home problems anyway, and they should say no if you do ask them. So don't put them in that position. Come ask me. I know exactly where I'm okay saying, no, you need to do the rest on your own. So when in doubt, come talk to me or somebody else who's in this class, not previous students, not tutors. Does that all sound fair? Like I said, it's two problems. First problem, I give you a bunch of data. And I say, do some calculations in the spreadsheet. Plot some stuff. Give me a trend line. Stuff that we've done before. What's the standard deviation? And then it has you do an algebra problem at the bottom. E is a stretch. You all should be able to do A through D. So 8 of the 10 points on this problem, A through D, should be not too much trouble. You should be able to do this. You probably knock out A through D in under half an hour if you're current on knowing how to make your charts and do your calculations like we've been practicing. You need to review some things, maybe it takes an hour. It's not too bad. E is hard. I'll help you with E if you come asking for help, if you're ready for it and you put in some time on your own. Don't come to me asking for help if you haven't at least tried it on your own. And then a gas laws word problem. It's got some pressure, it's got some temperatures, it's got some volumes. Do some gas laws calculations, turn it in, you get 10 points. These are designed so that pretty much anybody who's been here doing the work in this class should be able to get, call it 16 out of 20 here, right? I don't anticipate everybody's going to get E. So even if you don't even try E, and then you make a sig fig error here or there, or make a calculator error in one of your other spots, you can still get 16 pretty easily. So decent score for this. This should bring up everybody's grade and bring your exam grade into something that you're satisfied with. Questions about the take-home? Not yet? All right, it'll open up at noon. So you'll be able to start working on it whenever you want. Turn it in by next Friday before midnight. And again, just in case people haven't heard me say this before, if Canvas gives you trouble attaching an Excel file and then attaching pictures on top of it, sometimes if there's different file types, Canvas struggles depending on your phone or your computer or whatever you're submitting from. If you run into that issue, do it as 2 submissions. Submit your Excel file once and then go to resubmit and submit your paperwork. Right? Because I can see both submissions. On your end, I know it looks like you're overriding your submission, right? I can see both submissions. So if I see that everything's there except an Excel file, I'll go look at your other submission and it'll be there. Right? So worst comes to worst. I mean, if you really needed to, if it really won't let you submit things, you could submit it 5 times if you needed to. 4 pages of paperwork and 1 is an Excel. I'll still see everything. That's fine. I don't think anybody's ever had it that rough before, but that's like a worst case scenario, right? Worst case scenario, you can email me and attach the files. I hesitate with that one, mostly because one, then it's not tied to your Canvas, and so it's easier for me to lose it in my email inbox because I do have like 4,000 unread emails, 3,960 something, I think, right now. So it's things get lost in my inbox. They don't get lost when they get submitted on Canvas. So that's your best option. But if you really are up against the wall, you don't have the technology or something, then yeah, of course, email me, and I'll remember to make sure I hit receive or send you a message saying received, and I'll attach it as a comment to your file if need be. All right, so the technology should not be limiting everybody because I think we're all conversant with Canvas at this point, to the point where we can do that. Everybody been taking a look at the practice test so far? Only one thing left that we're missing, and that's practice with pH. We have covered everything other than, but that's fine. So all we're doing today is we're going to do some practice with acid-base reactions. So quick review. Let's review our acid nomenclature and our polyatomic ions real quick, because you can never have too much review of nomenclature. It's one of the first things you start to forget as soon as you're done with the polyatomic ions quiz, right? So how do we name our acids? It's all based on the suffix of the anion, right? So as long as we know what our polyatomic ions are, we can get our acid nomenclature. So it's 8 turns into ick, ite turns into us, and ide turns into hydro ick. So what polyatomic ion is this? Chlorate? Chlorate's O3. So it's the perchlorate. So that means we drop the 8. So it's perchloric acid. How about Br minus? What is that name of that ion? It's bromine with a negative charge, which means bromide. So that means we're right here, right? So it's hydrobromic acid. PO4 with a 3 minus charge is phosphate. This is one of those ones that's a little bit of an irregular. It's not phosphic acid, it's phosphoric acid. On the in-class test, if you wrote phosphoric acid, all right, so I won't commit either way, but I would understand that'd be a very minor deduction. That'd be would not be a full minus a whole point for that. Because phosphate to phosphoric acid actually does make more sense, but this is the right answer. What is this? Carbonate. So carbonate, carbonic acid. What's the formula for nitrate? NO3 with a negative charge. So that makes this nitrite because it's the same charge, just missing one oxygen, right? So ite turns to OUS. So nitrite turns to nitrous acid. And then here's our only other irregular, really. That's sulfate, right? But it's not sulfic acid. We put that extra syllable back into it, just like phosphoric acid. So instead of being sulfic acid, it's sulfuric acid. Right, and this is, we've been here for 11 weeks now. We've been in chemistry, immersed in chemistry, thinking about chemistry, going to chemistry labs, dealing with chemistry reagents, reactants. Sulfic should sound funny by now. Sulfic doesn't sound like a real thing. You've heard of sulfuric acid. Nobody's heard of sulfic acid. So you're starting to get to the point where you have what's called unconscious competence, which in other words means you're developing chemical intuition. You have an idea of, I'm not quite sure why yet, that doesn't sound right. So when you hear sulfic or phosphic and it sounds funny to you, trust yourself. You've been doing this for 11 weeks now. There's probably a reason why it sounds funny to you, why you've never heard that before. Okay? All right, questions on nomenclature? All right, so let's do another practice problem. Write out the reaction for carbonic acid. It's an acid-base reaction with carbonic acid reacting with sodium hydroxide. What would that look like? So carbonic acid, we just had it on the last page, right? H2CO3. We're being picky. It's going to be aqueous. Fun fact, if you drink club soda, you're drinking aqueous carbonic acid. Carbonic acid is actually why carbonated water tastes a little bit sharper than tap water, than flat water. It's because when you dissolve CO2 into water, it naturally reacts with a water molecule to make a carbonic acid molecule. So you actually drop the pH, make it more acidic, just by putting CO2 into a solution with water. Sodium hydroxide, NaOH. We didn't specify a phase for this one. So it could be aqueous, could be solid. I'm just gonna say aqueous for the sake of continuity. We don't usually drop solids into aqueous solutions. We don't. Sodium hydroxide is not a great compound to deal with as a solid. Because remember those hydrates that would pull moisture out of the air to fill their crystal structure? Sodium hydroxide is a compound like that, except it will go further than just making a hydrate. It'll actually pull enough moisture out of the air to dissolve itself and make itself into a solution. It's what's called hygroscopic, meaning it seeks out water. So basically, we don't deal with sodium hydroxide as a solid very much if we can help it, because it always dissolves in water. Not really relevant to the rest of this problem, but interesting nonetheless. It's basically what those silica gel packets are doing too. Those silica gel packets that keep things dry, they're hygroscopic as well. They pull moisture out of the air, similar to a hydrate. All right, what's going to happen? What kind of acid-base reactions can happen here? How do we know what's the acid and what's the base? Well, we named one as an acid. That's a pretty good indicator, right? It's got lots of H pluses that it can give up. What's going to act as a base here? What can accept an H plus? Well, is an H plus and Na plus, are those going to be attracted to each other? No. But the hydroxides. So the H plus and the hydroxide will react together. What happens when an H plus and a hydroxide react together? What do we get? H2O. Plus and a minus add up to 0. We stuck an extra hydrogen on there, so we have 2 hydrogens, 1 oxygen, and the whole thing's neutral. So we can be pretty sure that our acid is going to give away an H plus to the hydroxide. So what does that look like when we write it out? H2CO3 plus NaOH is going to make water. What's left of the acid after it gives up an H plus? If we pull an H plus off of the carbonic acid, we get what? 1 hydrogen left still, right? That's another polyatomic ion we know, right? So we just took 1 H plus away here. We gave it to the hydroxide, so we are left with hydrogen carbonate. Then what else is still floating around too? Sodium ions. So if this whole thing is all aqueous, I kind of mixed and matched. Remember we talked with the precipitation reactions about the ionic form versus the molecular form? I kind of mixed and matched the molecular form and the ionic form over here. Because the point that I'm trying to make is that our base or our acid just gives up a single H plus to become the conjugate base. There's actually 2 possible answers to this. This is what happens first, but the carbonate still has another H plus attached to it, right? If we had this reaction happen and then we still had more hydroxide around, our hydrogen carbonate can act as an acid too. So if this whole thing happened twice, now we've got sodium hydrogen carbonate plus more sodium hydroxide. That's going to make water again, right? We still have another H plus that it can give up. So the hydroxide can take it. We still make another water. And now it's not hydrogen carbonate, it's just carbonate. Now we have 2 sodiums floating around, right? So really it'd be Na2. So acid-base reactions, for the most part, are generally going to be 1-to-1 because they happen sequentially. If you have something like carbonic acid, excuse me, that has more than 1 hydrogen to give up, it doesn't give them all up at the same time. It does it in steps. So all your acid-base reactions are always going to look like you take one H plus, you give it to a base. If you still have another H plus, you can write it again. We can combine these two if we wanted to. So the overall reaction would be if we combine these two and we said, okay, I'm going to write the overall reaction. Both of these happening in a row would look like H2CO3 aqueous plus NaOH aqueous. And my bad handwriting just reminds me to let everybody know on the polyatomic ion quizzes, there are still a few of you who had written your capitals and your lowercase letters really similar to each other. We want to make sure that our capitals are capitals and our lowercase are lowercase, right? That's one of the things that we're picky about it's one of many things we're picky about in chemistry class. And so I don't actually like that A written like that. I'm going to rewrite it and make sure it's very clear that it's a lowercase a. So if the carbonate loses both of the H pluses at once, how many hydroxides does it have to react with? Well, let's back that up. Let's just write what we're going to make first. We're going to make sodium carbonate, and we're still making water. So that's both of these happening in a row. We started here, we went through this, and then used our hydrogen carbonate as another reactant to do the same thing again. What's wrong with the green one? Bingo. First thing you should do when you look at a reaction is make sure it's balanced. We've got carbonate, 2 hydrogens. We need to be able to make 2 water molecules. Or if you just look at it in terms of the sodiums, there's 1 sodium on this side. There's 2 sodiums on that side, right? So we've got to do that. Now we're almost there. What's not balanced now? H2O. See, the H2O, the number of oxygens, right? Oxygens and hydrogens. We took 2 hydroxides to react. Each hydroxide reacted with 1 of those H pluses. So we made 2 waters, not 1. All right. Luckily for you, you don't need to worry about this on the test, right? Because I'm going to write the reactions out for you. All you have to do is check that they're balanced. Usually the acid-base reactions, everything's going to be a 1. Everything's got a coefficient of 1. But there are a few ways I can write an acid-base reaction that looks like this, where there's a 2 in there because something had 2 H pluses to give up. Or for instance, if calcium hydroxide was involved, because calcium hydroxide has 2 hydroxides, so that's going to throw off our balancing, right? So you want to check it, but we do also want to understand that these steps happen sequentially. You lose 1 H plus and then the other. All right, let's talk about pH. Everybody loves logs, right? Nobody loves logs. I don't even love logs. Logs are complicated. They're hard to think in terms of logs. Mostly because logs are made up. I mean, everything's made up a little bit, but logs are made up because they're basically just there so that we can do algebra with exponents. Right? If you think about what a log actually is, the whole point of a log is so that you can solve for a variable that's in an exponent. Right, so if we had an algebra expression that looked like 10 to the x equals 1,000. If you're used to thinking in base 10, you can guess what x is, right? What is x? 10 to the what is 1,000? 10 to the 3, right? But just being able to look at it and do it in your head is not a good way to solve algebra problems, right? So if it wasn't a clean number like this and we wanted to solve for x, we need a tool for that. So that's what logs are. Logs are just the way we solve for what's in the exponent. And so if we took the log of both sides here, and so we need it to be the log base 10, and then we'd get log base 10 of 1,000 on this side. It's not exactly what's happening, but you can basically think about those canceling out. Right, so when you plug this into your calculator, we're going to get x equals log base 10 of 1,000, which we can plug in our calculator. So the calculator you're going to use for the test, know how to enter logs, because sometimes the order of the buttons changes depending on what calculator you're using. All right, so I know I'm emphasizing the log base 10. The log button on your calculator is log base 10. There's two log buttons on your calculator. There's log base 10, and then there's natural log, written as ln. ln is really log base e. And in other countries, they actually just write, if you just write log, it means log base e. E is like pi, it's an irrational number. It's at 2.17 something, 2.71 actually, I think. Doesn't matter. Point is, we don't want natural log for pH because pH is a base 10 scale. So you're just going to find your log button, and you either have to type in 1,000 and then hit the log button, or you have to hit the log button and then type 1,000 and then hit enter, depending on your calculator. So play with it, make sure you get the right answer, because our answer should be 3 in this case. That's the wrong eraser. All right, so we use log-based scales when we have a really wide range of possible values. Because, like we've talked about before, we like to keep our units in the realm where we can wrap our head around what those numbers are, right? So if you remember back to where we were on Monday, we ended talking about this H2O plus H2O reacts to make H3O plus and hydroxide. And we said, okay, well, those two concentrations are always going to multiply together to give us the same number at room temperature. We could say Kw is equal to concentration of H3O plus times concentration of OH minus. Does anybody remember what the value was for Kw? Anybody have their notes from Monday? pH scale goes between most of you, if you've been taught about the pH scale at all, you've been taught that pH goes between 0 and 14. Which isn't strictly speaking right. But that comes from this number right there. Right? What this means is that your hydronium concentration can be anywhere from basically 10 to the minus 14 up to 1. That's a huge range of values, right? Talking about concentration is as our molarity is 1.5 times 10 to the minus 8. It's hard to wrap your head around. It's hard to do math with that because that's a lot of zeros. So the pH scale was basically invented, and all log scales are basically invented when there's a really wide range of possible values. Anybody else think of a different log scale other than pH? We live in California, famously home to what type of natural disaster? Well, wildfires, that's more recent. I was going for earthquakes. All my relatives and in-laws from the Midwest are always, oh, California. Aren't you worried about the earthquakes? Not really, because they have a huge range of possible intensities, right? So we use the Richter scale for them, which is a log-based scale. The way log-based scales work is that if you go up 1 unit on a log-based scale, that's equivalent to a factor of 10, a 10 times more intense in terms of earthquake. So a 5.0 earthquake is 10 times larger than a 4.0. And a 6.0 earthquake is 100 times larger than a 4.0. 4.0 is about the threshold where you can actually feel it. A 6.0 is big. 7 is really big. I want to say the largest on record is an 8 point something, because an 8 point something is more than 10,000 times greater than a 4.0. Right? So because earthquake can have such a huge range of magnitudes, we use the log scale. Same for concentrations of acids. The other common log-based scale is decibels. Sound has a huge range as well. So I don't think decibels are log-based, but bells, the base unit of decibels, is log-based. So going up 10 decibels is a factor of 10. And going up 20 decibels is a factor of 100. Which is what allows us to measure sound on the same scale when it's a whisper versus an aircraft taking off. We can still use decibels for either of those because it's a log-based scale. So all that to say, logs are a pain, but there's a reason. Right? And in this case, our log-based unit that we're going to work with is called pH. So P is what's called an operator. This lowercase p, an operator is basically it's still a mathematical way of saying it, but it's basically a different way of saying it's a function. So like when you're in your math class and you see f of x, that means you're going to do some math to x, right? Whatever x is, you're going to do some arithmetic with it. P is just another function. And P specifically means you're going to take the negative log base 10 of something. Right? And it can be of anything. You can actually, it's not just pH. pH is defined as negative log base 10 of hydronium concentration. But you can have POH as well. POH is still taking the negative log base 10 of something. It's taking the negative log base 10 of, take a guess. Hydroxide. So remember that these square brackets in chemistry mean molarity. We're talking concentration here. So pH, POH, if you take a biochem class, they might hear about pKa. pKa is just another, you're taking the negative log base 10 of, in that case, of an equilibrium constant as a way to measure how acidic a specific compound is. All right, so if these two numbers are the same, if we have a neutral solution, we're going to go back over that same derivation we ended with, because I rushed it at the end of class on Monday. if we have the same value, if we have just pure water, and water can act as an acid and a base towards itself, we've got some amount of hydronium and some amount of hydroxide in our pure water, right? If hydronium and hydroxide are the same concentration, what do they have to be? Well, let's just call it X. We have X X times X equals 10 to the minus 14. So if we wanted to solve for X, we combine these two, we get X squared, right? So X squared equals 10 to the minus 14, which means to solve for X, we square root both sides, right? Square root of 10 to the minus 14, good catch, is 10 to the minus 7. So in water, in a neutral solution where we have equal amounts of hydronium and hydroxide both have concentrations of 10 to the minus 7 molarity, 10 to the minus 7 moles per liter. And when we take the negative log of 10 to the minus 7, remember log base 10 solves for what's in here, right? So that means that pH in a neutral solution is 7. What's pOH in a neutral solution? We have hydronium, but we also have hydroxide, right? Anytime you have a pH, you also have a pOH. Because you can't get around the fact that if you're in water, both of these are present. Now, if they're both present in the same amounts, it's neutral, which means our concentration of hydroxide is also 10 to the minus 7. So pOH is also 7. Right, so that's why it's neutral. We don't say that that water is neutral because it has no acid and no base. We call water neutral when it has equal amounts of acid and base. Because hydronium is how we measure acid and hydroxide is how we measure base. All right. Here's another useful form of the same equation. This equation right here is where we got our original concentrations, right, for a neutral solution. If we take the negative log of both sides here, we actually get the same equation rewritten a little differently. We can use laws of logs to pull them apart. This is the math class. I'm not teaching you the laws of logs. I don't think I could come up with all of them off the top of my head anyway. Doesn't matter. Because if you take the negative log of both sides and do a little rearranging, you get this version of the equation. In water, specifically at room temperature, it varies a little bit if you're not room temperature. We're going to assume everything's at room temperature for now. pH plus pOH will always equal 14. So how is that useful? Well, it means as long as we have one of these two concentrations, we can always get pH. Right? So we don't need to know hydronium concentration if all we have left is hydroxide. If we have hydroxide concentration, we can get pOH. And if we can get pOH, we can get pH. If we have acid, on the other hand, we don't have a measurable amount of hydroxide. It's there, but it might be too small for us to measure. If we don't have a measurable amount of hydroxide, then we must have some acid present. And if we know what the concentration of the acid is, we also know pH. Right? So the big step here is just logs are scary. I get that. Nobody likes logs. All you need to know how to do for logs for this class is understand that pH means take the negative log of a concentration, and POH means take the negative log of hydroxide. All right, before we move on, we're making an assumption here. Well, we're not, you are not yet. I'm about to make an assumption. How do we know the hydronium concentration of an acid? You ever see hydronium written on a chemical bottle in the in lab? We've seen all sorts of acids written on the reagent bottles. We never see hydronium listed though, right? It's because hydronium only exists in water. If you want to add H pluses to water, they turn into hydronium. Because if you have something that can give away acid or give away H pluses, and you have a ton of water molecules around, the water molecules just grab an H plus. So more likely the H plus gets stuck to one of the lone pairs on the water molecule. So when you put HCl in water, HCl is an acid that basically is so good at giving away its H plus that it gives away all of its H pluses to the water molecules. It doesn't, water is the base in this case. And if HCl gives away an H plus to water, what does the water turn into? Hydronium. And what does the HCl turn into once it's lost its H plus? Right, so for this class, the acids that I'm going to ask you about in pH questions are what we call strong acids. Strong acids, strong in the chemistry sense, does not mean more concentrated. Strong means that the reaction happens 100% of the way to completion. It doesn't stop partway. Most acids are what we call weak acids, which means this reaction doesn't go 100% to completion. That's one of many reasons why you might not get 100% yield when we're talking about percent yield problems, because reactions that don't go 100 all the way to completion are going to stop. You're going to have leftover reactant, basically. In our hamburger analogy, you stopped cooking hamburgers once you got enough of them made. That doesn't mean you ran out of reagents necessarily. It just means that you stopped cooking. The strong acids don't stop cooking. The strong acids go until they're gone. And there's 7 strong acids. They're the only ones I'm going to ask you pH questions about for this class. Again, when you take Gen Chem, if you take Gen Chem, there's a whole 6 weeks where we talk about equilibrium, which is how do we know how close to completion does a reaction go. For now, just I want you to know that there are strong acids, and they're the ones I'm going to ask you about. So HCl, HBr, HI, so hydrochloric, hydrobromic, hydroiodic, perchloric, chloric, nitric, and sulfuric. Those 7, those are the ones you know right now. There's, again, just like our polyatomic ions, this is not an exhaustive list of strong acids. These are the most common strong acids that are based on the polyatomic ions that you know. There are other strong acids out there. These are the ones that I'm going to ask you pH questions about. because these are the ones where we can assume it completely turns into hydronium when you put it in water. So as long as we're talking about a strong acid, as long as you know the concentration of the acid, you also know the concentration of the hydronium. Because what's our balancing look like here? Everything's got a coefficient of 1, right? That means for every 1 mole of HCl you put into a solution, you get 1 mole of H3O plus out of it. So if we know this concentration, we also know this concentration because it's 1 to 1. So one practice problem, then we'll take our break. So if we have a solution where HCl is, concentration of HCl is 0.010 moles per liter, what's the pH? Well, pH is negative log of hydronium concentration. And HCl is our strong acid. It was on that list I just covered up. If it's a strong acid, we can say concentration of HCl is equal to concentration of H3O plus. Because if you put 1 molecule of HCl in the solution, you get 1 molecule of hydronium within sig figs. So our pH for this solution is negative log of 0.010 moles per liter. So you need your calculator. Maybe you don't. You might be good at doing logs in your head. If I give you nice even numbers. Two last notes. What do we do with units and what do we do with sig figs? I've got good news for you on both of those fronts. When you take the log of something, basically the units disappear. So pH units is the unit. So actually just writing it like this, you just have to say what the number is. You have to say pH equals, but then there's no units behind it, kind of like a percentage. The other thing we care about is sig figs. And the other good news here is, well, this is mixed news. There's a whole nother set of rules for exponents with sig figs. For exponents and logs, there's a third set of rules. In addition to addition, subtraction, multiplication, division, the good news part of it is that I'm not going to make you memorize that. It's a whole different system. So for pH, always, for this class, always write it to the hundredths place. Even if it comes out to be an even number, still add your zeros to the hundredths place. If you're interested in the sig figs and why we do that, I'm happy to talk to you about that, but I don't want to confuse the issue right now, right before the test. Well, a week before the test. So for this class, just always write to the hundredths place for your pH. So you don't need to worry about units. You don't need to worry about sig figs. That makes pH easy, right? All right, let's take a break. Let's come back at 11:35.
Yes, follow this for me, and I think the big issue is I don't understand why from the They're hydrogen.
So most of these bonds where we have something electronegative attached to a hydrogen, for the most part, it turns out to be oxygen in our common cases, right? But in any case, basically you get something where you get a really electronegative, large difference in electronegativity, which means this bond actually behaves more like an ionic bond.
Oh,
So basically the chloride doesn't hold the H plus very tightly. It's more like the H plus is stuck to the chloride because the chloride has all this electron density. So
but
you
even in that, how is it that sodium is more, I guess you could say like that. It would be less.
yeah, so sodium's less electronegative.
Oh, makes sense now. All right.
So basically, acid-base reactions are just the H plus getting bumped from one area of high electron density to another, where it's more closely bound.
All right.
Good question.
I know.
No problem.
And then if we get in that stage, we can do senior assessment. And we do like. He was like, what we said, because we realized it. Yeah, he was like, yes, nothing to. You know, it was. We need to say we should. It's like, we can do it. And everybody goes, it has to be with an angel. And then after. He's so funny. Give it 40. You can in my room, take my bed. I know those, he got out of that.
All right, so, sorry, did you have a question? What's up? The polyton finance part? I mean, it's better than nothing. I can give you a couple points for it. You want to take it before lab today? Okay. Thanks for following up. So that works too. Just show if I'm not in lab 15 minutes early, then just come back to my office. You know what my office is. Yeah, we're office hours tomorrow night. Yeah, for sure. It's hard to find time for all the stuff you have to do, right? Yeah. All right. So as we're coming back from break, this is a really important slide because this is how pH shows up on the final. Right? You have an acid-base reaction, and the question is, what's the final pH? So for these type of questions where we have a strong acid reacting with a hydroxide, it's an excess reactant question. We need to know which of these is left over and how many moles per liter it is. Because if our end goal is calculate the final pH, we need to know either concentration of hydroxide at the end or concentration of H3O plus at the end. If we can get one of those, we can get pH. So it's an excess reactant problem. I'm not actually on the test, I don't even make you do that part. Right, I'll give you the products. But for now, for practice, what do we get when nitric acid reacts with lithium hydroxide? It should seem really similar to that carbonic acid question or the HCl in water earlier. When you put an acid and a hydroxide together, what do they make? Water, every time. These are called neutralization reactions because you're taking a base and an acid and you're making something that's neither. Right, so hydroxide plus an H plus gives us H2O. And then what else is left over? The H plus from the nitric acid and the hydroxide from the lithium make the water. So we get lithium nitrate. Still aqueous, still just floating around. So we need to know what runs out first, and we need to know how much of the excess reactant is left. to answer this question. So that's what makes it a little bit of a different wrinkle. It's not a theoretical yield question. It's an excess reactant question. What are my leftovers? And how many do I have? So if you're unsure where to start with stoichiometry problem, what's the first thing you should do? Make sure it's balanced first, but then convert to moles. Like I said, most of these acid-base reactions, everything's 1-to-1. It looks good, right? Just like this. So we are balanced. Then the question is simply, how do we get everything to moles? So if we're given us grams, we know what we're doing to get that to moles, right? Molecular weight. So 0.325 grams. Molecular weight for lithium hydroxide is going to be, lithium's really close to 7. I think it's what, 6.98 or something. 6.94, thank you. Plus 15.999 for the oxygen, plus 1.008 for the hydrogen. Which gives us a total of 22.95-ish. 23 points. All right, give me one more sig fig on that. 0.9.
5.4 seconds.
We only have our uncertainty to the 10th to the 100th place here, so we would want to round it to 5. Right, because we're adding. So then we can say, okay, for every 1 mole of lithium, or sorry, got that backwards, we need grams to cancel out, right? So for every 23.95 grams of lithium nitrate, that's 1 mole for lithium hydroxide. And as far as our nitric acid goes, we've got 125 milliliters. The solution with the concentration, so we're going to use that concentration as a conversion to get to moles. There's 1,000 milliliters in 1 liter. And for every 1 liter, that's 0.100 moles. So I believe that gives us 0.0125 moles. How many sig figs do we get to keep here? Got 4 sig figs there. This is exact, so it's infinite sig figs. Ooh. Waiting. So then, but then that's measured, so we only get the 3 sig figs. Right, reminder, concentrations are also measured numbers. So your concentrations are going to factor into your sig figs. What did we actually get for a number over here for the lithium hydroxide?
6 times 10.
146.
3 6.
Okay, so far so good. Little molecular weight calculation, a little concentration calculation. Everything's 1-to-1, so that actually makes finding the limiting reactant really easy, right? Because we're using everything up at the same rate. If everything's 1-to-1, we can just say, oh, I have less nitric acid, therefore I run out of it first. Because our coefficients are all 1. If our coefficients aren't all 1, we can't say that. So if we wanted to show our work for it, we could say 0.0125 moles HNO3. And every 1 mole of HNO3 means 1 mole of LiOH used. Right? Because this is just our stoichiometry step. So we're just looking at the coefficients. We said 1 mole of nitric acid because it's got a coefficient of 1. 1 mole of lithium hydroxide used because lithium hydroxide has a coefficient of 1. Do we have that much lithium hydroxide? We have at least that much lithium hydroxide? Yeah. So that means that our nitric acid is running out first. There's our limiting reactant. If we want to know how much lithium hydroxide is left, we just need to know how much we started with and how much we used. We know both of those numbers, right? So 0.0136 moles LiOH minus 0.0125 moles used, 0.0011 moles left. So far, so good. So far, this is nothing new, right? We haven't focused on excess reactant problems in a little bit. We've been more focused on theoretical yields, but this is all stuff we've seen before. Maybe we didn't like it last time we saw it, but at least it's not new. We wrote the complete reaction. We found the limiting reactant. We found the excess reactant, including how many moles we have left. Last step, calculate the pH when the reaction is done. How do we get to the pH from moles of hydroxide? We have two ways to get to pH, right? We either have pH is equal to negative log of hydronium concentration. We don't have a number for the hydronium concentration, so we can't use that. At least not yet. Our other equation on your equation sheet that gets us to pH is pH plus POH equals 14. So if we don't have acid left over, then we don't know anything about hydronium. Instead, we know hydroxide. So we want to find POH to get to pH. So we need final concentration of hydroxide. All right, the most common mistake I see with pH questions. We just found how many moles are left, right? To get POH, we just take the negative log of that, right? No. We need this as a concentration before we take the negative log of it. So we need moles per liter. So 0.011 moles of hydroxide left. What's the volume of the solution? Well, we didn't have a starting concentrate or starting volume for the lithium hydroxide, right? You said grams. What does this actually look like though physically? If we were doing this in lab, this would mean we took 0.3 grams and we added it to a solution, right? So our 0.3 grams are now sitting in this 125 milliliters. So our final volume is 125 milliliters.
Would the 3 grams or 0.225 grams add to the volume of?
No, turns out. In extreme cases, you can see that volume change a little bit when you add solid, but for most cases, if we're not anywhere close to the saturation point, adding a solid to a liquid doesn't change the volume of the liquid within sig figs. In some cases, it actually makes things smaller. And if you take 50.0 milliliters of ethanol and you mix it with 50.0 milliliters of water, you get 98 milliliters total. Because no, it's basically that there's a little bit of empty space in between the molecules, and when you put a mixture of two different things together, they can fill in the gaps a little bit better.
So it's not like when you're sitting in the tub and your weight displaces the water.
Right. It's not just really, it's not additive if we're careful about the sig figs. So for this part, we're just going to assume that I'm not going to give you one of those exceptions. So whatever tiny change in volume you might have, we're just going to say it's lost in the sig figs. So 125 milliliters, 0.125 liters. So 0.011. I lost a zero, yep. Thank you. 0.011 over 0.125.
Lithium.
So, good question. The same way that we can say if it's a strong acid, we can say that the concentration of the acid is equal to the concentration of hydronium. If it's an ionic compound, if it's 1 mole per liter of lithium hydroxide, that means it's 1 mole per liter lithium and 1 mole per liter hydroxide. Because we're going to assume that these ionic compounds, when we put them in water, they split up 100% of the time. All right, so if you wanted to show the math for that, it would look like the 0.0011 moles LiOH, and for every 1 mole of LiOH, that's 1 mole of hydroxide. If it's not 1-to-1, calcium hydroxide is the common one that gets used. It's a strong base, meaning it dissociates 100%, but there's 2 hydroxides for every mole of calcium. So in that case, this is not 1-to-1, that would be a 2-to-1. So you would have to show that step. Okay, my moles of hydroxide in that case are not the same as the moles of the entire ionic compound. But in this case, because lithium hydroxide, 1 mole of lithium hydroxide has 1 mole of hydroxide, because it's 1-to-1, we can just say this. All right, we're almost there. What do we still need? We have concentration of hydroxide at the end. We're trying to get to pH. Here's our 2 methods for getting to pH. We're using this one because we have hydroxide. So we take our hydroxide concentration and we get POH. POH is negative log of hydroxide concentration. So negative log of 0.0088. So something just above 2.2 or so. 2.0. So 2.06. We're always going to take these to the 100th place. So if POH is 2.06, last step, and it's an easy one. 14 minus 2.06. So again, we've gotten into the realm of all of our problems are long problems now, that all the individual steps we know how to do. This is the newest one. What I want you to remember is anytime the question is asking about pH, you have to use one of these 2 methods. You either need a hydronium concentration or you need a hydroxide concentration. If you can get either of those, we're there. Right, and just to reiterate how it shows up on the practice test, it's going to be on number 7, 8, or 9. It's number 9 on the practice test. It'll probably be number 9, but I might switch up the order to make sure that you're reading and not memorizing the order. And How kind of me. I gave you the hardest one on the practice test. Remember how I said that if it's calcium hydroxide, we have that 2-to-1 issue? So you get to practice it on the practice test. But this is exactly what we just did. Determine the pH formed by adding grams of a solid to a solution with a known concentration. Right, so literally the same problem with different numbers. The last wrinkle I could conceivably throw at you on this problem is instead of it being a solid added to a solution, if it was two solutions mixed together, which doesn't really change much. It changes how we get to the moles for this one, and it changes our final volume at the end. Because if it was instead of 450 milliliters, where do I keep setting these? Where's the other one? If instead of writing it like that, if I said 455, let's make the numbers cleaner. If we said it was 250.0 milliliters at whatever, 0.065 moles per liter, we still know how to get to moles from that, right? The only thing that changes is that at the very end, when we're trying to get concentration of whatever is left over, our final volume is not just going to be 450, it's going to be 450 plus 250. Because we mix two solutions together. So if you're mixing two solutions together, then we add the volumes. If it's a solid added to a solution, that's the volume at the end. All right, so I'm not going to solve this one now. I think I have a key for you that's ready to publish this afternoon or tomorrow afternoon, actually, on the practice test. So take a stab at solving this on your own and before you check the key. And then I'm happy to work through it step by step like we just did on Monday during our review session. Right, so our last scheduled lecture is Monday, 10:15, just like normal. And it's just review, no new material. It's almost the same problem as the practice.
When you said about house double, you're saying that the double the mole amount concentration?
It just basically means any of those 1-to-1 stoichiometry steps that we did aren't 1-to-1. Now they're 2-to-1. So we actually need to show them and make sure the units cancel out to make sure we're, because it might be doubling in some places, it might be dividing by 2 in other places. So it just means we need to be careful and we need to show all of our stoichiometry.
That would happen in balance.
It would, exactly.
Yeah,
So
you don't have to stress.
now it's balanced, right?
Yeah.
So I get 74.092. for molecular weight. Right, so 74 just came from our masses on the periodic table, right? Just doing molecular weight, we've done that lots. If you're still a little bit shaky on that, ask me about it. So that gives us our moles over here, 0.00982. Then we have 1.00 liters of our hydroiodic acid. For every 1 liter, that's 0.020 moles. So 0.020 moles. Wasn't it nice if we could give you 1 liter solution? That makes life easy, right? So what's going to run out first? Yeah, we're using the hydroiodic acid up twice as fast, but we have more than twice as much of it. But because it's not a 1-to-1 ratio, we still want to show our work for this to make sure we didn't do something wrong in our head. If we're pretty sure it's going to be the calcium running out, we say, okay, well, 0.00982 moles of calcium hydroxide. And every 1 mole calcium hydroxide means 2 moles HI used. I think I doubled that properly. Carrying numbers is always tricky, doing it mentally. But we're only going to keep 3 sig figs, right? How do I know that that's moles of HI used and not moles of HI produced? Where is HI in the reaction? It's a reactant, right? Before the arrow. Everything before the arrow is an ingredient getting used up. Everything after the arrow is being made. Right, so that's why I'm able to just put used right there, because both of these are on the reactant side. So how much HI is left? Well, 0.020 moles HI minus 0.0196. Oh, that's right. I needed to throw an extra. We'll keep 1 extra sig fig on this, because otherwise it's going to give us an answer that doesn't make sense. I mean, it does make sense, but not to you yet. Everybody with me? Is that enough to find pH yet? Almost. I would say. When you do the subtraction, I think it comes out to be 0.0004, but maybe I did the subtraction wrong. We're just taking the moles that we started with and we're subtracting the moles that are used. Which if we had enough hamburger patties to make 200 and we actually made 196, that'll do it. Good news about that type of errors is if you show all your work properly and then get the wrong answer, one, I know you're not using AI, and two, it's only a 1 point deduction at most. And so if you did everything right but got the wrong answer because you just punched in 169 instead of 196, I can tell what you meant to do. And that's an easy mistake. Anybody could do that. So if we're trying to get to pH, we have moles of HI left. HI was one of our strong acids. Not that you need to necessarily be clocking that right now because I already told you I'm only going to ask you these questions about the strong acids. So we need to either use pH equals negative log of H3O plus, or we have to use pH plus POH equals 14. Which one makes the most sense right now? Why? But we used it all up, didn't we? So we have acid left over. If we have the acid left over, we're going to use this method. We can go straight to pH. We need it as a concentration, but we can do that. So when you have acid left over, you use this version. Because having the acid left over means you can get straight to concentration of hydronium. If you have the base left over, you have to get POH and then use this. So going back to somebody's quiz question that I answered a couple weeks ago when we first learned stoichiometry, everybody's always desperate for me to just give you a procedure for a stoichiometry problem. There's just too many types of stoichiometry problems. That trying to give you just one procedure for all of them, the procedure itself would be so complicated that it's not worth it. Think about the logic. We're trying to figure out excess reactant. We're trying to figure out what's left over. Depending on what's left over, that tells us which method we have to use to get to pH. So concentration of hydronium. Is moles of acid over the total volume. Moles of acid left, I guess I should say. We have that number. We just found that number. What's our total volume? We had a solid being added to a solution, so the volume of the solution is our total volume. And it's just 1 liter, so that makes life easy. So our pH is negative log of H3O plus, which is the same as our concentration of the acid because it's a strong acid. So pH is negative log of 0.0004. We get something like 3.6. All right. Sometimes I'll put a little table like this. And it's mainly to remind us that as long as we can find one of any of these pieces, we know the rest of this box. We know the rest of the table. We found hydronium concentration, 0.0004. If we know the hydronium concentration, oops, I put that in the wrong box, didn't I? If we know the hydronium concentration, we know the pH. If we know pH, we also know pOH, right? So pOH in this case is going to be 10.61? 14 minus pH. Which also means we can get that number. You just have to undo the pH piece, which we have 6 minutes left on the clock in our last lecture. I don't think it's all that relevant. We don't really need it for either of the two tests you have left. But if you wanted to get pOH here, pOH was negative log of hydroxide concentration. So if we wanted to reverse that, we can say concentration of hydroxide is equal to 10 to the negative pOH. Right, all I did was I took pH and I moved the pOH and I moved the negative over, and then I raised 10 to the power of both sides. That's how you undo a log. It's not a math class. I'm not going to ask you about that. That's just for your own personal edification. Good job this quarter. You're almost done. One more week. Hard push. I'll see some of you in lab in a few minutes, and I'll see everybody else on Monday.